Hello, everybody. We're going to talk for a few minutes about how to design good mathematical theories. Now, Fred, when he talks about this, he uses the image of a potted plant, actually a potted palm tree. But I don't like that image. I like this image instead, partially because I get to draw it, which is kind of fun. This, in case you did not know, and I know you did, this is a giraffe. And what makes a good giraffe? That is the question that I want to ask. What makes a good giraffe is that a giraffe has to be tall, right? Short giraffes are bad. Short giraffes are bad. I'll just say it. Short giraffes are bad. We want tall giraffes. We need beautiful, tall giraffes. In the world of math, that means that we want theories that build on top of each other for a long time, right? We want to understand a lot of math from each theory that we develop. We want to understand a lot of the world. So we want nice, tall giraffes. And you can think of the length of the giraffe's neck as being made up of different theorems. So the more theorems we can put together, the taller our giraffe is, and the more wonderful it is. Now, at the bottom of the giraffe, all these theorems, they have to stand on something, and we need giraffe feet. And our giraffe feet look somewhat like these triangles. Our giraffe feet, we typically want to be small. We want small feet. Now you're saying to yourself, why do we want small giraffe feet? Why don't we want large giraffe feet? Well, because if we had large giraffe feet, our giraffe would look ridiculous. It would look like he's walking around with flippers on. And we don't want that. We want a nice, slender, tall giraffe. It's a wonderful thing. Now, what these feet represent in our world of math, these feet represent all of the definitions and postulates we need. Definitions and postulates. Right? And so we want not too many of these, right? We don't want to have a lot of things that we have to take on faith. We want just a few of these. And then we want a lot of stuff that we can prove based on that. Okay? Skinny feet, tall giraffe. Skinny feet, tall giraffe. That's what we want. Okay, here's what we don't want. We don't want a lot of definitions and postulates, because if we have a lot of them, then that makes all of this kind of clunky and fat. We don't want that. We want to have a nice, tall, skinny giraffe. Now, what does this mean? Well, I'll tell you. So in this chapter, we are about to explore the concept of a polygon. Now, a polygon is just any multi-sided figure like that, okay? Could be any kind of shape, really. It can have as many sides as you want. And when we talk about calculating the polygon's area, we need to have a rule that allows us to do that, right? And we want the number of rules that we have to take on faith. That is, we just have to believe them. Those rules should be small in number. They should be tiny little giraffe feet, right? Not too many things that we just have to believe. So, when we're talking about the polygon, P in our book has come up with 3 different postulates. Every polygon has an area. So that is, if you have this polygon, it is possible to calculate an area. Okay? If you have congruent triangles, those have equal areas. Congruent triangles have equal areas. Okay, that's a good thing to know. You can add the areas together if they don't overlap. Okay, so I can add the areas together. So watch this. I'm going to take this, I'm going to have this triangle here, and I'm going to be able to calculate a area based on my formula of A equals 1/2 base times height, right? And then I'm going to have this triangle here, and I'm going to have this triangle here, and I'm going to have this triangle here, and I'm going to have, how am I going to do this exactly? I'll have this triangle here, I'll have this triangle here, and I'll have this triangle here. There we go. I have only triangles. So if I can find the area for each of these triangles and add them all up, then I know the area for the whole polygon. That is what P is proposing here, is that I can add together those areas so long as they don't overlap. We need one more postulate. That is, we need one more formula that we take on faith that allows us to determine everything else. When P first started writing her list of postulates, she had all sorts of formulas. She had the A equals 1/2 BH formula. She has the A equals length times width formula. She has the A equals 1/2 A plus B times H formula. But this is starting to give our giraffe big feet. This is a lot of stuff for us to put down here. And the fewer things we can put down here to build our theorems on, the better our theory is. So we want to have as few as possible. Fred says that we can do it in just one formula. Fred says we need this formula. That is, the area of a square equals S squared. Now, why is this important? I'll tell you why. Because you are about to enter into a very difficult series of your turn to plays. We have 3 of them. We have the your turn to play 260. We have the your turn to play 263. And we have the your turn to play 264. And what all of these your turns to play are doing is they are letting you experiment with what formula you want up here. Okay? What formula do you want in this? So for instance, in the your turn to play 260, we are going to suppose that we know this formula. 1/2 base times height. And then can we calculate the area of any polygon, of any shape at all, like that? Can we calculate it just knowing this theory? And do we like that? Or would we like to look at the theory of parallelograms, which A equals BH? Do we want this to be our formula that goes in there? I don't know. Do we? Well, in this one, we get to consider, well, maybe we want to turn everything into rectangles, and we want to use the rectangle theory. This is all just playing with what the world would be like if these were the theorems that made up the 4th postulate. So you're just playing with math. You're just experimenting with what would the world be like if I had to turn everything into a parallelogram? What would the world be like if I had to turn everything into a rectangle? Fred says that eventually the theorem or the postulate that we're going to have here is going to deal with squares. A equals S squared. But for these your turn to plays, first we're going to experiment with using these as our basis. So I hope that kind of makes sense, and you can understand what the point of doing these your turn to plays are. Good luck.